Welcome back, everyone, to part 2 of our presentation, Foundations of AI, an Introduction to Artificial Intelligence through Cutting-Edge Papers. In part 1, we explored the foundations of AI reasoning through logical agents, first-order logic, and inference mechanisms. Today, we'll continue our exciting journey, delving into how AI systems represent and organize knowledge, how they plan and make decisions in complex environments. And we'll look at the cutting-edge research shaping the future of AI. Whether you're joining us from part 1 or starting here, I'm thrilled to have you with us as we complete our overview exploration of AI's cognitive capabilities. Let's dive in. Here's our roadmap for part 2 of our presentation. We'll start with a brief recap of the key concepts from part 1 to set the context. Then we'll explore two main areas: knowledge representation, focusing on how AI systems organize and structure information, and automated planning, which deals with how AI makes decisions and formulates plans. We'll conclude with a look at future directions in AI research, tying together all we've learned across both parts of the presentation. This structure will complete our overall understanding of how modern AI systems think, reason, and act. Once again, we're going to use this format in terms of presenting papers, individual papers, to highlight topics that we want to discuss. So in the following segments, we will examine a carefully curated collection of technical and peer-reviewed papers that align closely with our part 2 agenda. Just like part 1, I have assembled selected works to have them serve as the foundation for illustrating key points and synthesizing high-level concepts pertinent to our discussion. For your reference and to facilitate further exploration, each paper is clearly cited on each respective slide. This approach ensures that you have ready access to these valuable resources should you wish to delve deeper into any particular topic or concepts presented. So, okay, back to our subject at hand. So this slide is an introductory slide. Knowledge representation. Knowledge representation is a fundamental aspect of AI, focusing on how information can be structured and stored for efficient reasoning and retrieval. It's crucial for enabling AI systems to understand and interact with complex environments. There are several key approaches to knowledge representation, including semantic networks, which represent knowledge in patterns of interconnected nodes and arcs; frame-based systems, which organize knowledge into structured chunks; ontologies, which provide a formal specification of concepts and relationships in a domain; and finally, knowledge graphs, which represents knowledge in a graph structure of entities and relationships. Each of these approaches has its strengths and is suited to different types of knowledge and reasoning tasks. Challenges in knowledge representation include scalability, handling very large knowledge bases, dealing with uncertainty and incomplete information, and the difficulties of knowledge acquisition and maintenance. Recent trends in the field include integrating knowledge representation with machine learning techniques, developing distributed knowledge representations that can be shared across multiple AI systems, and exploring multimodal knowledge representation that can integrate information from different sensory modalities. These developments are crucial for creating AI systems that can understand and reason about the world in more human-like ways. Here's our first paper from Nicole et al.'s 2016 review titled A Review of Relational Machine Learning for Knowledge Graphs. This paper provides a comprehensive overview of relational machine learning techniques by knowledge graphs. These methods allow AI systems to learn and reason about relationships between entities, crucial for tasks like link prediction or knowledge-based completion. The authors discuss various models from tensor factorization approaches to neural network-based methods. They explore how these techniques can be used to create low-dimensional embeddings of entities and relationships, making it possible to perform efficient reasoning over large knowledge graphs. The paper also covers the application of Markov logic networks to knowledge graphs, combining probabilistic reasoning with first-order logic. These techniques have wide-ranging applications, including powering question-answering systems, enhancing recommendation engines, and improving semantic search capabilities. This work highlights the growing importance of knowledge graphs in AI research and applications, showing how they can be used to represent and reason about complex, interconnected information. This next paper is by Hogan et al.'s 2021 paper, simply named Knowledge Graphs. It provides a thorough overview of knowledge graphs. They discuss the structure, creation, and applications of knowledge graphs across various domains. The authors define knowledge graphs as large networks of entities, their semantic types, properties, and relations. They explore methods for creating and curating knowledge graphs, including both manual and automated approaches. The paper also delves into reasoning techniques over knowledge graphs, which allow AI systems to infer new information from existing knowledge. Knowledge graph refinement. The process of improving the quality and coverage of the graph is another key topic. The authors highlight applications of knowledge graphs in diverse areas, from powering search engines to accelerating drug discovery and detecting financial fraud. However, they also point out significant challenges, including issues of scalability when dealing with massive graphs, ensuring the quality and trustworthiness of the information, and integrating data from diverse and potentially inconsistent sources. This comprehensive overview underscores the central role that knowledge graphs are playing in modern AI and information systems. Hamilton et al.'s 2017 work, titled Representation Learning on Graphs, Methods and Applications, focuses on representation learning on graphs. This involves learning low-dimensional vector representations of nodes or subgraphs, which can then be used for various downstream tasks. The authors discuss methods like matrix factorization, random walks, and graph neural networks. These techniques aim to capture the structural information in graphs in a format that's amenable to machine learning algorithms. The paper distinguishes between transductive methods, transductive methods which can only generate embeddings for nodes seen during training, and inductive methods which can generate embeddings for previously unseen nodes. This is crucial for applications involving dynamic graphs. The authors highlight applications in areas like node classification, that is, predicting properties of nodes, link prediction, that is, forecasting the formation of new edges, and graph classification, aka categorizing entire graph structures. However, challenges remain in scaling these methods to very large graphs and in handling graphs that are dynamic or heterogeneous in nature. This work has had significant impact in areas like social network analysis, recommender systems, and bioinformatics, where graph-structured data is prevalent. Zhai et al.'s 2021 survey, A Survey on Knowledge Graphs, Representation, Acquisition, and Applications, is another great paper. And it provides a comprehensive look at knowledge graphs, from their representation and acquisition to their wide-ranging applications. They discuss various knowledge graph embedding techniques which allow for efficient reasoning over large-scale knowledge graphs. The paper also covers methods for structuring and expanding knowledge graphs, including both manual curation and automated extraction from unstructured data. An interesting focus is on temporal knowledge graphs, which can represent how facts and relationships change over time. The authors highlight applications in areas like natural language processing, where knowledge graphs can provide semantic context, and in recommender systems, where they can capture complex relationships between users and items. The paper also discusses the use of knowledge graphs in question answering systems, enabling more sophisticated reasoning over factual knowledge. Looking to the future, the authors identify several promising directions, including the development of cross-lingual knowledge graphs to bridge information across languages, improved representation of common sense knowledge, and tighter integration of knowledge graphs with neural language models. Yes, that's what I meant. This survey underscores the growing importance of knowledge graphs as a versatile tool for representing and reasoning about complex, interconnected information in AI systems. Du et al.'s 2019 paper, titled Cognitive Knowledge Graph Reasoning for One-Shot Relational Learning, is another interesting paper that you may want to look at. This paper introduces cognitive knowledge graph reasoning for one-shot relational learning. This approach allows AI systems to quickly learn new relationships from just a few examples, mimicking human cognitive abilities. The authors propose a method that combines traditional knowledge graph techniques with meta-learning approaches. Their system can induce rules from limited examples, transfer learning across different relations, and iteratively refine the induced rules as more evidence becomes available. This cognitive-inspired approach offers several advantages, including the ability to rapidly learn new relationships and improved generalization from few examples. These capabilities are crucial for creating more adaptive and efficient AI systems that can quickly incorporate new knowledge. However, again, always challenges, and there are remaining challenges in handling complex multi-hop reasoning tasks and in scaling the approach to very large knowledge graphs. This work represents an important step towards more flexible and human-like learning in AI systems, potentially enabling applications that can quickly adapt to new domains or quickly incorporate new knowledge in dynamic environments. Automated planning. Let's get into this new topic. Automated planning is a branch of AI that focuses on the realization of strategies or action sequences, typically for execution by intelligent agents, robots, or autonomous systems. It's about making decisions on a course of actions before acting. A planning system typically includes a state representation describing the current situation, action models defining how actions change the state, goal specifications describing the desired outcome, and planning algorithms define a sequence of actions to achieve the goal. There are several types of planning, including classical planning, which assumes a fully observable deterministic world, probabilistic planning, which handles uncertainty in action outcomes, and temporal planning, which considers the timing of actions. Key challenges in the field include handling uncertainty and partial observability in real-world environments, and scaling planning algorithms to complex, high-dimensional domains. Recent trends in automated planning include the integration of planning with machine learning techniques, the development of explainable planning systems that can justify their actions, and research into multi-agent planning for coordinating multiple autonomous entities. These advancements are crucial for applying automated planning to real-world problems in robotics, logistics, and other domains requiring intelligent decision-making. So let's take a look at this paper that is relevant to automated planning. This is by Garrett et al.'s 2021 survey named A Comprehensive Survey on Task and Motion Planning for Intelligent Robots. It provides a comprehensive overview of task and motion planning for robots. This field deals with the challenge of not just deciding what actions to take, that's task planning, but also how to physically execute them, that is motion planning. The integration of these two aspects is crucial for creating truly autonomous robots that can operate effectively in complex, real-world environments. The authors discuss various approaches, including hierarchical planning methods that break down complex tasks into simpler subtasks, sampling-based methods that effectively explore high-dimensional configuration spaces, and optimization-based techniques that can handle complex constraints. The paper highlights applications in areas like manufacturing automation, where robots need to perform complex assembly tasks, household robots, where systems must navigate cluttered environments and manipulate diverse objects, and autonomous vehicles which need to plan both routes and detailed motion trajectories. Key challenges in the field include scaling these methods to very complex environments with many objects and constraints, and developing techniques for real-time planning in dynamic settings, where the environment can change unpredictably. This survey underscores the critical role of task and motion planning in advancing the capabilities of intelligent robotic systems. Wang et al.'s 2021 paper named Learning and Planning in Average Reward Markov Decision Processes explores learning and planning in average reward Markov Decision Processes, MDPs in short. This approach is particularly suited for long-term planning in continuous environments like robotics or resource management. Unlike episodic reinforcement learning, which optimizes for a finite horizon return, average reward MDPs aim to maximize the long-term average reward, making them suitable for ongoing tasks without clear terminal states. The authors introduced new algorithms, including differential Q-learning and average reward policy gradient methods that can handle the challenges of these domains. These techniques are particularly valuable for problems where the long-term consequences of actions are critical, as they avoid the pitfalls of discounting future rewards too heavily. Applications of this work include robotics control, where a robot needs to maintain optimal performance over extended periods. Resource management scenarios where long-term sustainability is key. And continuous manufacturing processes that need to be optimized over time. This research represents an important step in developing AI systems that can plan and make decisions with a truly long-term perspective, crucial for many real-world applications. Argyll et al.'s 2009 survey, titled A Survey of Robot Learning from Demonstration, while older, meaning it's an older literature, remains highly relevant in discussing robot learning from demonstration. This is an important paper. This approach allows robots to learn new skills by observing human experts, potentially accelerating robot programming and adaptation. The authors discuss various methods for gathering demonstrations, including kinesthetic teaching, physically guiding the robot, teleoperation, and passive observations. They also explore different approaches to deriving policies from these demonstrations, such as direct policy learning, where the robot directly mimics the demonstrated actions, inverse reinforcement learning, where the robot infers the underlying reward function, and behavioral cloning, where the robot learns a mapping from states to actions. The advantages of learning from demonstration include the ability for non-experts to intuitively program robots and faster skill acquisition compared to manual programming, for sure. However, challenges remain in generalizing learned skills to new situations, handling suboptimal or inconsistent demonstrations, and ensuring safety when learning potentially dangerous tasks. Despite its age, this survey laid the groundwork for much of the subsequent research in imitation learning and remains a key reference in the field of robot learning. Kober et al.'s 2013 paper, titled Reinforcement Learning in Robotics, a Survey, review of reinforcement learning in robotics provides a comprehensive overview of how these techniques can create adaptive and self-improving robotic systems. The authors discuss the application of Markov decision processes to robotics, exploring both policy search methods, which directly optimize the robot's behavior, and value function approximation techniques, which learn to estimate the long-term value of actions. They highlight the unique challenges of applying reinforcement learning to robotics, including the need to handle high-dimensional continuous state and action spaces, the importance of sample efficiency when learning on physical systems, and the critical need for safety and stability during the learning process. The paper covers applications in areas like motor skill learning, where robots can acquire complex movements, autonomous navigation in unknown environments, and robotic manipulation tasks. Looking to the future, the authors identify promising directions such as transfer learning between different tasks, meta-learning approaches that allow for quick adaptation to new situations, and hybrid approaches that combine model-based and model-free reinforcement learning. This work underscores the potential of reinforcement learning to create more flexible and adaptive robotic systems, while also highlighting the significant challenges that remain in bringing these techniques to real-world robotic applications. Grigorescu, I don't know how it's pronounced, and again, forgive me if I'm pronouncing these authors' names incorrectly. This is a 2020 survey named A Survey of Deep Learning Techniques for Autonomous Driving. It explores the application of deep learning techniques to autonomous driving. They discuss how deep learning is used in various components of autonomous driving systems, from perception and localization to planning and control. In perception, deep learning methods like convolutional neural networks, CNNs, are used for tasks such as object detection and semantic segmentation, allowing the vehicle to understand its environment. Recurring neural networks, RNNs, are applied to tasks requiring temporal reasoning, such as predicting the future trajectories of other vehicles. Generative adversarial networks, GANs, are being explored for generating realistic training data and for handling rare events. The authors highlight challenges in the field, including ensuring the safety and reliability of deep learning models in critical driving scenarios, handling rare events and edge cases that may not be well represented in training data, and improving the interpretability of deep learning models to understand and trust their decisions. Looking to the future, the paper discusses promising directions such as multimodal sensor fusion to combine data from different types of sensors, the use of reinforcement learning for developing adaptive driving policies, and the integration of explainable AI techniques to make the decision-making process of autonomous vehicles more transparent. This is the last item that is being worked on quite a bit now. Explainable AI, to make sure that decisions are transparent. This survey underscores the transformative potential of deep learning in autonomous driving, while also highlighting the significant technical and ethical challenges that need to be addressed for widespread deployment. All right, the conclusion slide already. As we conclude our two-part journey through AI's cognitive capabilities, we can see several emerging trends and key themes. There's a growing convergence of symbolic and neural approaches, as seen in neurosymbolic AI and logical neural networks. This integration promises to combine the strengths of logical reasoning with the flexibility and learning capabilities of neural networks. Scalability and efficiency in reasoning and planning remain critical challenges, especially as AI systems are applied to increasingly complex real-world problems. Handling uncertainty and partial information is another key theme, with probabilistic approaches being integrated into various AI techniques. Explainability and interpretability are becoming increasingly important, especially as AI systems are deployed in critical applications. Looking to the future, we can expect continued progress in neurosymbolic AI, pardon me, potentially leading to more robust and generalizable AI systems. Large-scale knowledge integration, combining information from diverse sources and modalities, is likely to be a major focus. The development of AI systems with common sense reasoning capabilities remains an important goal. potentially revolutionizing human AI interaction. As AI becomes more and more prevalent, ethical and responsible AI development will be crucial. Future research directions may include developing AI systems capable of continual learning and adaptation, improving multi-agent coordination and collaboration for complex tasks, enhancing human-AI interaction and collaboration, and applying AI to scientific discovery and creativity. As AI systems become more capable and ubiquitous, addressing ethical considerations and ensuring the development of beneficial AI will be paramount. In conclusion, the field of AI is advancing rapidly, pushing the boundaries of what machines can perceive, understand, and do. So we continue this exciting journey. We're not just creating smarter machines. We're gaining deeper insights into the nature of intelligence itself. The challenges ahead are significant, but so are the potential benefits for society. Across both parts of our presentation, we've explored the fundamental building blocks of AI reasoning, the sophisticated ways AI represents and organizes knowledge, and how it plans and acts in complex environments. These advances are not just theoretical anymore. They are shaping the future of technology and our interaction with intelligent systems. Thank you for joining me on this overview exploration of AI's brain, so to speak, from logic to robots and beyond. Again, I included 2 reference slides with the main references that I'd like to show you. If you like to freeze the video and look at them, please feel free. This is the first reference slide. That was the second one I went over. And this is the end of the presentation. See you in our next AI ML presentation series, and thank you very much for watching. Goodbye.